There's Boltzmann thermodynamics. Actually, the Boltzmann equation is engraved here on the headstone. The entropy, the absolute entropy can be calculated. It's equal to Kb. Kb is the Boltzmann constant, which is 1.3807 times 10 minus 23rd joules per Kelvin. Ln W. W is the number of ways you can arrange the system. It's a positional ways. So W is kind of related to the more ways, the less constrained. The fewer ways, the more constrained. The most constrained system will be a perfect crystal. A perfect crystal at 0 Kelvin has only one way of arranging the atoms. The atoms have to be in the perfect position, and the temperature is 0 Kelvin, so the atoms can't move. What happens is if you increase the temperature of a perfect crystal, the atoms are going to start to vibrate. If the atoms start to vibrate, then there are more ways you can position the atoms in three-dimensional space. So, here, the lowest entropy we can have is if there's only one way to arrange everything. The natural log of 1 is 0, and so 0 will be the entropy. That would be the absolute 0 of entropy with just one way. Now, as we get to more complicated things, there are more ways to arrange things. So that's what's going on at the beginning of chapter 13. At the beginning of chapter 13, 13.1, they're dealing with microstates. Each microstate is one way of arranging this, what we call the system. Did I talk about system and surroundings? Okay. So if I have these 5 colored balls here, and then these energy states, how many different ways are there to arrange it? And here, if I promote one of these balls up to the first energy state, then there are 5 different configurations that we have, and the number of ways is 5. Here, if they're all in the first energy state, there's only one way, although we can flop the positions. These are just color-coded. They're all the same atom or whatever they are. And so we can count the number of ways. If we can count the number of ways, like there's 6 ways here, there's 5 ways there, there's 1 way there, we can figure out the entropy. This is going to have the lowest entropy because there's only one way. But the more ways we have, the less constrained things are, and the greater the entropy. So if we have 5 ways of arranging things, it's going to have a higher entropy. If we have 6 ways of arranging things, it's going to have an even higher entropy. And so this is going to be dictated by that. Problem is we don't deal with 5 atoms. We deal with moles of atoms. If we're dealing with moles of atoms, then there are going to be a lot of ways we can arrange things. And so let's look at this one here. The Boltzmann equation, equation 13.1, is deceptively simple. It suggests that S can be calculated simply by enumerating the possible microstates, the number of ways. As demonstrated earlier, the enumeration of microstates is straightforward when the system contains only 5 particles. For a system of containing a mole of particles, the number of microstates defies comprehension. So if we have a mole of particles, how many different ways are there to arrange it? So it's 10 to the 23rd. 10 to the 10 to the 23rd is huge. And so punch that in your calculator, what are you going to get? Some ridiculous. I don't know. Like calculate if you could do that. What would the number be? This number is not only incomprehensible but also uncountable. It's uncountable. So when people who do this kind of stuff use statistics, and this is called statistical mechanics, or statistical physics, or statistical thermodynamics. This is set with such large number of particles, they can't count them individually one by one. And so, even though the Boltzmann equation is fairly simple, this is not the way we determine entropies. We want to determine what entropy, in other words, we want to quantitate what the entropy is because there's two driving forces in nature. One's the energy, the other is the entropy. We want to maximize the entropy, so in order to figure out how entropy plays a role in things, we need to be able to quantitate it. And so when we're looking at a particular reaction or process, or whatever system we're looking at, we're going to have a delta S, and the delta S is going to be the final entropy minus the initial entropy. And so the final entropy is usually, if we're looking at a reaction, it's going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. And then we can see how the entropy changes. Does the entropy go up? That's what we want for a spontaneous reaction, or does the entropy go down, or maybe it didn't change at all. And so there are two ways of getting this. This is called the absolute entropy. The first thing is this. Delta U is equal to U final minus U initial. And these are called the absolute internal energies. And delta H is equal to H final minus H initial. The problem with absolute internal energies and absolute enthalpies is they're too difficult to calculate accurately. And so we typically never do a calculation like this, and we never do a calculation like this because the absolute internal energies and enthalpies, this enthalpy, this internal energy, are difficult to calculate accurately. Difficult to determine accurately. The reason they're difficult to determine accurately is because of this. What is the absolute zero of internal energy? Well, we get the absolute zero of internal energy is the combination of kinetic energy and potential energy. So the absolute zero of kinetic energy may be somewhat straightforward. That would be 0 Kelvin. At 0 Kelvin, we should have 0 kinetic energy. But is it really 0? Because, at 0 Kelvin, the atoms stop moving, the molecules stop moving, everything stops moving, except for the electrons. Do the electrons ever stop moving? No, electrons can't stop moving. That would be a violation of the Heisenberg uncertainty principle. And so electrons don't stop moving. That's called the 0 point energy. What is that 0 point energy? The electrons don't, what is that? It's not 0, is it? Well, it can't be 0, is it? And then potential energy. What is the absolute zero potential energy? The absolute zero potential energy is, there's energy stored in lots of different things. So, for example, if we look at water, if we look at a solid block, a perfect crystal ice water at 0 Kelvin, then we have potential energy stored in the hydrogen bonds that hold the water molecules in their perfect position. And then we have potential energy stored in the bonds. So we got to break the hydrogen bonds, we got to break the bonds. And then we have potential energy stored with electrons. Electrons are held to the nucleus. And then we have potential energy stored in the nucleus. The protons and neutrons are held together by a nuclear binding force. And do you have potential energy stored in the protons? Do we have potential energy stored in the neutrons? In other words, can the protons and neutrons be broken into even smaller particles? Yes, quarks, but where does it end? Maybe it ends at quarks, is that right? And the quarks, do they have any potential energy themselves? And so, what is the absolute zero of energy? And when there's no more energy. And so, that's the problem. Here we know what the absolute zero of entropy is. And we can figure out the absolute zero of entropy is 0. But here, it's hard to figure out because, what is the absolute zero energy? And therefore, we never use this, but here we'll use this because of the third law of thermodynamics. Because of the third law of thermodynamics, we can use absolute entropies to determine it. Now, how do we figure out what the absolute entropies are? There are two ways to figure out the absolute entropy. One is we could use the Boltzmann equation. S is equal to KB ln of W. And just calculate it. So one, we can try to calculate it. But figuring out, can you imagine figuring out how many different ways you can arrange things positionally? It's way too much. And so we're never going to do this, except for this, when it's super easy like this, then we can do it. And this calculation, there's only one way. It's easy. Or two, we're going to determine it experimentally. How do we determine absolute entropies experimentally? Well, it turns out that entropy is going to be related to heat. So, for example, if we think about the heat capacity of water versus the heat capacity of copper, it takes a lot more heat to warm up water than it does to warm up copper metal. Why is that? Well, it takes a lot more heat to warm up water because there are a lot more ways that water can absorb energy. Water can vibrate, it can rotate. This S is equal to KB ln of W. KB ln of W, which is here. Or log of W. We could do log, it just change K, natural log to log base 10. And what's the other one? Question? Determine experimentally. The way we determine it experimentally, heat capacity methods. When you heat up water, there are lots of ways water can absorb that energy. It can cause vibrations, it can cause rotations of the water molecules, and it can cause translations. When you heat up copper, when we heat up copper, the only thing that happens is it causes vibrations. There are no translations because it's not molten, it's solid. And there's no rotations because they're spherical. The atoms. And so heat capacity is going to be related to it. And so what we're going to have is, we're going to have this. We're going to have that the entropy is going to be related to Q over T delta T. And so let me show you here. So what we're going to do, we're not actually going to do this, but basically the entropy is going to equal this. This is from calculus. This is called an integral. And then the heat, Q is heat, T is the temperature. The heat that's going to be absorbed is going to be related to Cp, the heat capacity. And so we measure heat capacities at different temperatures. And then take the area under the curve, the heat capacity curve. And so let me show you that, if I can. This is actually delta S. And then this is going to be from 0 to T. And so it's going to end up kind of being like the final temperature minus the initial, but the initial temperature is at 0. And at 0 Kelvin, the entropy should be 0. So this is just going to be T final. And so we're going to get the entropy at T final here is what we're going to end up with. And that's going to be this. It's just related to heat capacities. You don't have to know the math for this. But basically, the heat capacity for water is going to look something like this. Heat capacity for water is around 2. And then for ice, this would be ice. And then it jumps up to about 4 for water. And then it drops down to about 2 for steam. Heat capacities here. What this symbol means is we take the area under the curve. So if you want the entropy of water, we measure the heat capacities at various temperatures, and then we determine the area under the curve. So if we want the entropy of water at 298 Kelvin, we go to 298 Kelvin and then just sum up the area here. That would be its entropy. That's what the map tells us over there. If we want the entropy of steam, it'd have a higher entropy because we have to take the area of this entire region here under the curve. And so for steam, it's going to have a much higher entropy because it's going to encompass this entire area here. And so we can get the entropy of H2O at different temperatures here by taking heat capacity measurements here and then plotting them out and then determining this. Obviously, we aren't going to take heat capacity measurements at 0, but because of the first, third law there, we can figure out it's got to be 0. But we can take heat capacity measurements at temperatures, very cold temperatures here. Delta here, it just means a very, very small. This D, small, very small, compared to the full-size delta. Infinitesimally small D. And so this is what we have here. Okay, so what we're going to do is we're going to determine all these entropies and then compile them into a table here. The table is Appendix D. So let's take a look at Appendix D here. Now we could get the entropy at many different temperatures, but that would be just way too much data to have. And so if we have the entropy of H2O at many different temperatures, we're looking at a huge data table, but this data table is just going to pick the most common temperature. The most common temperature that we work at will be room temperature. Room temperature is going to be at 298 Kelvin. And so this is going to be a compilation of entropies. This is absolute entropy at 298.15 Kelvin. This is the most convenient temperature. Now, if we change the temperature, that'll change the entropy. Well, the higher the temperature, we expect a higher entropy. The lower the temperature, the lower the entropy. And here we have the heat capacity here at 298.15 Kelvin. So we measure heat capacities at many different temperatures. And you can see the heat capacity and the entropy are somewhat related here, as they should be. All right. So let's take a look at the entropies here. And if we look at some of the entropies here, like for example, aluminum solid. Aluminum solid should have a fairly low entropy at room temperature. Room temperature is this crystalline metal. And so its entropy is fairly low. 28.33 is pretty low. Let's compare that to dialuminum hexachloride gas. These are molecules. that has a fairly high entropy of 490. The units for entropy are joules per mole Kelvin.
I'm confused.
Mm-hmm.
Like, what do these numbers mean exactly? Does it help out with like the solubility constant, like the KSP and everything? We knew that like if it was like 1.8 times 10 to the negative 5, it was more product favored or reactants favored. Like, is this something like that?
Yeah, we're looking at the patterns here.
Okay.
And the patterns is this. Let's take a look at the solid. Aluminum solid, 2033. ALF3 solid is 6644. AlCl3 solid, 110.7. So let's look at the solid. This solid is fairly high, 239. Barium, 62.8. Barium carbonate, 112. Barium chloride, 123. Barium fluoride, 96. Barium oxide, 70.42. Barium sulfate, 132.2. Beryllium is very low. Look at that, 9.5. It's pretty low. That means it's well ordered. The lower this number is, the better ordered it is. And so we expect for solids to be well ordered. Beryllium chloride, beryllium fluoride, beryllium oxide, 82, 53, 14. Bismuth, 56. Bismuth trichloride, 177. Or bismuth chloride, bismuth oxide, 151. Boron, 586. We look at the lowest ones here. Like, if we look at carbon, diamond, 2.38. It's very low. This is our room temperature, not 0 Kelvin.
Is that the lower number?
The lower the number, the more constrained and the higher the order is. And so diamond is very well ordered solid because of its low entropy. So when we look at solids and look at their entropies, the entropies are roughly 0 to 100. Some are over 100, some are a lot over 100. Like calcium sulfate is about 100, but barium sulfate was quite high, over 200. But most of the solids, there'll be outliers, but most of the solids are in the 0 to 100 range. That means they're fairly well ordered. What about the liquids? Well, if we look at carbon tetrachloride, 216. What other liquids do we have? Let's try to find some more liquids. C3O2, which is 181. CS2, 151. Other liquids here. H2O liquid. H2O liquid is kind of low, because most solids are like, say, 0 to 100. H2O liquid is fairly well ordered. That's because of strong hydrogen bonding. So 6991 is kind of low. H2O2 liquid is still fairly low, 109. H2SO4 liquid, 156, so that's kind of typical for liquid. ICL liquid, 135. So basically, solids look to range from 0 to 100 because they're pretty well ordered. Liquids are going to have a higher entropy because there's going to be more disorder. They're going to have fewer constraints. They're going to have translational motion. And so liquids are around 100 to 200. They're going to be outliers here. What about gases? Let's take a look at gases. 247, 258, 260, 180. This is a pretty well ordered gas though because it's only atomic iodine. H2O2 gas 232. So when we look at gases look to range above 200. And so what we have is like solids 0 to 100, liquids 100 to 200, gases 200 to 300, and they're going to be outliers both up and down. Like for example, liquid water. Liquid water is more ordered than a typical liquid. And then there's solids. There's solids that are going to be more disordered than typical liquids too. And so there are going to be some outliers, but those are the basic ranges we have. And so how do we use entropy? How we use entropy is, solids are going to have lower entropy. What does lower entropy mean? Lower entropy means from 0 to about 100. Liquids have higher entropy. Higher entropy means maybe about 100 to 200. And gases have the highest entropy, to be about 200. That's how we're going to use it right now qualitatively. Quantitatively, we're going to use it to calculate changes in entropy. So if we want to calculate what was the change in entropy quantitatively, then we'll plug in the absolute entropies of the products minus the absolute entropies of the reactants. Where do we get the entropy? Somebody else measured it. Somebody else did the heat capacity measurements and figured it out. Or somebody else did some other thermodynamic calculations to figure it out. And so we have entropy here. And there are other ways you can determine entropy as well. And so those are entropies. Now, something weird happens, and that is this. What was the absolute zero of entropy? What was the third law of thermodynamics?
Perfect crystals at 0 degrees Kelvin is 0.
Yeah, the absolute entropy of a perfect crystal at 0 Kelvin is 0. So 0 is the most ordered. How many ways are there of arranging a perfect crystal? There's only one way of arranging a perfect crystal. Therefore, that's going to be the lowest number of microstates, lowest number of ways of arranging, and therefore the lowest entropy. So how can we have this? This must be a typo then. AM3 plus has an entropy of negative 321.7. So a negative entropy, what does that mean? Does that mean that aluminum ion aqueous is more perfectly ordered than a perfect crystal at 0 Kelvin? Could that be possible? I mean, this is more ordered than diamond. Diamond, had a positive entropy. Well, maybe it's a typo, so let's take a look and see. Yeah, it must be a typo. Do you see any other negatives? There's some more negatives here. Do you see negative 73.2, negative 53.1? Negative 56.9. There are a lot of negatives, actually. A lot of negatives. So what does that mean? Does it mean it's more ordered than a perfect crystal? That's doubtful. And so how can we have a negative? It's like this, is there such thing as negative 100 Kelvin? Can you have a temperature of a negative 100 Kelvin? Negative 100 Kelvin, not a temperature change. Of course, we can have a temperature change of a negative 100 Kelvin. We can lose 100 Kelvin. So let's say we start off at 373 Kelvin. We can have a negative temperature change and drop it down to 273 Kelvin. So we can go from 373 Kelvin to 273. But can we go from 0 Kelvin to negative 100 Kelvin? Is that possible? Yeah, 0 is the absolute zero. And so there's no such thing as negative Kelvin. What's the absolute zero of entropy? I just talked about. We don't know the absolute zero of internal energy and absolute zero of enthalpy, but we do know the absolute zero of entropy, which we need in order to do these calculations here. And the absolute zero of entropy was the perfect crystal, third law of thermodynamics. But this is a violation of the third law of thermodynamics because now we're having entropies even lower than absolute zero. Is that possible? No. So if somebody was saying, I have a negative temperature, let's say, what's the temperature outside today? The temperature outside is negative 10 degrees. They must be talking about not Kelvin, because that would be impossible. They must be talking about either Celsius or Fahrenheit, because those have what we call an arbitrary zero. not an absolute zero. And so the 0 point in Celsius is the freezing point of water. Okay, that's not absolute zero. That is the coldest temperature. Freezing point of water, we can get colder than that, right? Freezing point of water is just 0 or 32 Fahrenheit. Can we get colder than 32 Fahrenheit? Yeah, we can get to 0 Fahrenheit, but we can even get colder than 0 Fahrenheit. So that's what we call an arbitrary versus an absolute zero. So Celsius has an arbitrary zero that's just picked or chosen as the freezing point of water. What's the arbitrary zero for the Fahrenheit scale? How did they determine what 0 Fahrenheit is? So I know it's 0 Celsius. I have a reference point in my mind, but for 0 Fahrenheit, do you have a reference point in your mind? What exactly is 0 Fahrenheit? How cold is that? Well, it's got to be awfully cold, 0 Fahrenheit. I used to imagine this. I used to imagine there's some scientist, Lord Fahrenheit or whatever, and one day he goes outside and it's very cold. So cold that he thinks that's the coldest temperature ever and calls that 0 Fahrenheit. But was it the coldest temperature ever? No, it wasn't the coldest temperature. We could have negative Fahrenheit. You're going to get even colder. And so that's what I used to think. But now I know what 0 Fahrenheit means. It's the same thing with internal energy. How do you break down the atoms to cores? Can you break them down to even smaller, or is that it? That's the end. It's the lowest possible energy because you've broken everything apart. And so that's the problem with that, because what is the absolute zero there? So we pick an arbitrary zero sometimes. And the arbitrary zero for Fahrenheit turned out to be the freezing point of a saturated salt solution. So, when people make ice cream, they want to get colder than freezing. And so they make ice water, and the ice water can get even colder than that. And still have good thermal conductivity. So, well, it turns out that we've seen this before. There are 3 tables in one. When did you first see this? You first saw this here with delta H. You remember delta H here? And there's one very unusual delta H. There's one very unusual delta H is the delta H of formation of H plus. If we look at the delta H of formation of H plus, it's 0. What does that mean? Well, we know what a delta H of formation reaction is. The delta H of formation of H plus is for this reaction. It's for the formation of 1 mole of H plus aqueous from the elements in the most stable state under the conditions. So this means we have to form H plus aqueous from half a mole of hydrogen gas. In order to do that, we have to break the HH bond. So we take a half mole, we got to break the hydrogen-hydrogen bond. And then we have to ionize. This is going to cost energy. It's going to cost energy to dissociate. It's going to cost energy to ionize. But we're going to get some energy back. And the energy that we get back is from hydrating the ions, that is, making the aqueous ions and forming ion dipole attractions. But do you really believe that delta H, there's no energy change in this? This is essentially free. Do you believe that? No. This is arbitrary definition. Delta H of formation for this is arbitrarily set at 0. It's not really 0. It's just arbitrarily set at 0. Why is that? Why that is we have to think back to HCl. This is back in chapter 7, so this is still review. I'm still kind of a mix of review and new stuff. And so if we think back to delta H of formation of HCl. Let's go back here. So this is set by definition. And the reason is because of delta H of formation of HCl. If we form HCl, then we're forming 1 mole of HCl AQ from the elements in their most common state. So that would be hydrogen gas, most common of this, or the stable state under these conditions. And chlorine would be Cl2 gas. And so if we take hydrogen gas and chlorine gas, we can make HClAQ. And delta H for this we can measure. And delta H for this from calorimetry measurements will come out to minus 167.2. Here. Now this delta H of formation is going to be forming HClAQ. HCl is a strong acid, strong electrolyte. Strong electrolyte is going to form H plus and Cl minus AQ. So basically, what we're going to have here is delta H of formation for HCl is equal to the delta H of formation for H plus the delta H of formation for Cl minus. So I know what the combined total is. The combined total is minus 167. So out of that minus 167, how much of it is attributed to H plus, and how much of this is attributed to Cl minus? In other words, is it 50-50? You know, half this energy comes from the H plus, the other half comes from Cl minus. Is that correct? Maybe, maybe not. So we can estimate it using quantum mechanics, but you know, there's going to be errors associated with that calculation. And so what it is it's too hard to separate this. In other words, whenever we form a cation, we also form an anion. And so I can't do just the cation. It would be great if I could just do the cation. If I could just do the cation, then I can take calorimetry measurements and I can figure it out. But is it possible just to form a mole of H plus without any anion? No, it's impossible. In other words, can you have something be oxidized without the oxidizer present? No. And so there's got to be an oxidizer that takes the electron, and that oxidizer is chlorine. And so what we end up with is a problem of how do you divide this? You know, how much of this belongs to the first, how much of this belongs to the second? And so we don't know. And so the thing that people do is, well, they'll just call this 0. And therefore, this will be minus 167. So what they're going to say is 100% of this comes from chlorine, 0% of this comes from H plus. Is that accurate? No, that's not accurate. But the situation here is it's not going to be a problem. It's not going to be a problem because of this. It's not going to be a problem because this one is going to give us an error, let's say to the left. This one's going to give us an error to the right, but when I add these together, the error to the left cancels out the error to the right, and we get an accurate value. This is an accurate value for the sum total. In other words, the errors are going to be equal and opposite. So the error that I have for the cation will cancel out the error that I have for the anion. So essentially what we have is 3 tables in one. In other words, we have, let's say, the Kelvin, the Fahrenheit, and the Celsius. And so if somebody said, okay, what's a higher temperature? If somebody said, what's a higher temperature? And they said, okay, 101 versus 100. Which one's a higher temperature? 101 or 100? You'd say 101. But then I said, well, you're wrong. 101 is not a higher temperature because what I meant is 101 Kelvin versus 100 Celsius. 100 Celsius is boiling point of water. 101 Kelvin is super cold. And so you're wrong. But then you'd say, well, that's not a fair question because I didn't tell you the units, right? And you can't make that comparison. For sure, I'm not going to compare Kelvin and Celsius directly like that. That's not fair. But the problem with this table is, okay, what's a higher entropy? What's a higher entropy? Let me back up here. What's a higher entropy? 33.15 or minus 99.6? What's a higher entropy? You say, yeah, 33.5 is a higher entropy, right? 33.5. And then I say, wrong, because I'm saying 33.15 Kelvin and minus 99.6 Celsius. Then what would be the higher temperature? Well, minus 99.6 Celsius would be a much higher temperature than 33 Kelvin. And then you go, that's not fair, right? That's not fair. But your book is going to say, no, that is fair. Your book is going to say that's fair because you should be sophisticated enough to realize that this is 3 tables in 1. And so this is 3 tables in 1. That is this. Same thing goes here. Basically, what we're saying here is that it's 3 tables in 1. That is, the cations are all going to be offset because the cations have an arbitrary 0. This has an absolute 0. Aluminum has an absolute 0. What's the absolute 0? So this is Kelvin. And the absolute 0 here is relative to a perfect crystal at 0 Kelvin. And so the lowest entropy we can have here is 0. But when we look at aluminum 3 plus, this is minus 321.7. This is not the absolute entropy. This is the relative entropy. So this would be like the Celsius of entropies. And the Celsius of entropies are all going to have an offset. They're all going to be offset by 273. And then we have the anions. The anions, well, that's a cation. And the anions are going to be offset the opposite way. So rather than, let's say, having to add 273, we have to subtract 273. So the cations shifted this way, the error. The anion shifted the opposite way, the error. And so when I take a cation and an anion, then those errors cancel out, and I'm back to normal. And so the reason this works is you cannot form an anion without a cation. And you cannot form a cation without an anion. They have to come together. And therefore, it all works out. Sometimes you can form a cation without an anion if the anion cancels out as a spectator, but that's fine because we cancel out on both, and so we end up with an accurate result. And so the same thing happens with delta H's of formation. If we go back to hydrogen, H plus, this is wrong. It's offset one way. Here's HCl. Take a look at HCl is minus 167. H plus is 0. What do you think chloride is? And let's go back to chloride. Chloride is minus 167. So 100% of this went to chloride. So in other words, when we look at delta H's of formation, the same thing happens. But we can't form H plus alone, and we can't form chloride alone. We have to form them in combination. So one error is one way, the other error is the other way, and they cancel each other out. And this is the accurate number for HCl. And so we see this before. And therefore, there are 3 tables essentially in one. And these are the 3 tables. Okay, so the data for ions in aqueous solution are relative to values of 0 for delta H of formation for H plus. And so this is our arbitrary 0. This is like Celsius, setting the 0 point. This is not absolute zero, third law of zero. This is arbitrary zero for ions. And so we have to be careful when we compare the numbers, with delta H's formation for ions, just like we have to be careful when we compare the entropies. So there's no way we can compare this here. It's minus 321 Celsius versus 28 Kelvin. We don't compare those two numbers directly. We compare cations with cations, and we compare anions with anions, and we compare everything else with everything else. That's how we deal with this. Okay, the other thing that's forgotten a lot, because maybe you heard about this and forgot about it, but it didn't bother you because when you do the calculations work out. The same thing happens with entropy. But the other thing that's forgotten is, what does this little superscript mean? Here. That's going to be important in this chapter. In chapter 7, it wasn't that big of a deal because everything had that superscript there. Everything. And so it wasn't a big deal because if everything has a superscript, then you just go on your way doing the calculations that you've been doing. But in this chapter, not everything has that superscript, and it makes a big difference. So, for example, if we have this superscript versus if we don't have this superscript, changes how we'll do the calculation completely. And so what does that superscript mean? Well, that superscript means that we're doing this under standard thermodynamic conditions. What are standard thermodynamic conditions? So if we look at this is at 298.15 Kelvin. Is that standard temperature for thermodynamic conditions? It turns out there's no standard temperature. It just so happens that you can't have data at all temperatures, otherwise the data table would be infinitely huge. And so we have to limit the data. Well, we're going to limit the data to what's the most common temperature. The most common temperature is room temperature, not 0 degrees C. So there's no standard thermodynamic temperature because not everybody works at 0 degrees C. And not only that, not everybody works at 298. There are plenty of people who are doing high temperature reactions or low temperature. And so there's no standard temperature. However, there are standard thermodynamic conditions. And what are the standard thermodynamic conditions? These are that. So substances are 1 bar. So there's a standard pressure. The standard pressure is 1 bar. And then there's a standard concentration. Whenever we have a solution like this, the standard concentration is 1 molar. And so 1 bar, 1 molar. That's what that means. Now, do we do all reactions at 1 bar, 1 molar? No, we don't. Sometimes we'll do reactions at higher pressures and lower pressures, and sometimes we'll do reactions at higher concentrations and lower concentrations. Not everything's at 1 molar. And if that's the case, that's going to change this. And that means we can't use these values here without having to do some additional work. All right, so the basic message is entropies of solids are around 0 to 100. Entropies of liquids are around 100 to 200, and entropies of gases are about 200. Now, solutions can be fairly well ordered. So if we look at a solution like HCl, let's go back to HCl. It's fairly well ordered. Let's look at the entropy of HCl, aqueous. HCl gas is going to have a higher entropy, but it's still fairly well ordered. Most gases are above 200. If we look at HCl aqueous, this is in the solid range. Do you see that? So HCl aqueous is pretty well ordered, and that's because of the hydrated ions, hydrated protons, and hydrated chloride ions are fairly well ordered within the hydration sphere. So that entropy is pretty low. A lot of these aqueous solutions have fairly low. Fluoride we can't compare. We need the cation, so we can compare HF. So we can compare HF. Where we don't have HF aqueous here. But here. Now, how much of this 56.5 is due to the entropy of the H+, and how much of that 56.5 is due to the entropy of the chloride? Because the H+ is going to have some entropy because it can move. got translational motion. You can be in different positions. The same with the Cl minus. So should we say half the entropy is due to the H plus and the other half is due to the chloride? We can't say that because the solvation spheres, the hydration spheres, are going to be a little bit different. The attractions there. And in fact, it's very difficult to separate the entropy of H plus from the entropy of chloride because we can't form it individually. So we can't take heat capacity measurements on H plus alone. Right? It's going to be HCl. And therefore, what do we do? Well, what did we do with the entropy here? Take a look at this. We have a zero entropy. Is that zero entropy? That must mean we have a perfect crystal at 0 Kelvin, correct? But this is not at 0 Kelvin. This data table is at 298. So how can we have a zero entropy here? And in fact, the zero entropy is for H plus AQ. So H plus AQ must be better ordered than a perfect, well, actually equally ordered as a perfect crystal. There must be only one way of arranging H plus in water. And that one way is it's got to be perfectly positioned, maybe right dead center of the beaker. And so the H plus has to be fixed right dead center in the beaker. And then the hydration spheres, we got to have 2 waters, one directly above and one directly below, and then 4 waters, in an octahedral configuration. So it's got to be perfectly ordered and not move. It can't move. Because if it starts moving, then the entropy goes up. And so is this accurate? That is, H plus, there must be a second, this must be the 4th law of thermodynamics. The 3rd law of thermodynamics is the entropy of a perfect crystal at 0 Kelvin is 0. And the 4th law of thermodynamics must be the entropy of H plus, 1 molar H plus at 298 Kelvin is 0. Is that the 4th law of thermodynamics? No, it's not the 4th law. What do you think the 0 is? Do you think that's an absolute 0 or an arbitrary 0? In other words, do you think H plus really has 0 entropy? It's perfectly ordered? No. Its entropy's got to be a lot higher than this. So the entropy's got to be a lot higher than this. But we don't know it because of this. We know the entropy of the HCl. Is 56.5. But how much of this 56.5 belongs to H plus? And how much of this 56.5 belongs to Cl minus? Well, apparently 0 belongs to H plus, and let's see how much of the 56.5 belongs to Cl minus. We go to Cl minus, and all of it. So 100% of the entropy belongs to Cl minus, and 0% of the entropy belongs to H plus. Is that accurate? No, and the reason that is because it's an arbitrary 0. It's too difficult to figure out what proportion belongs. We could split it 50-50, but that's arbitrary too, because it's probably not 50-50. And so the easiest thing to do is just to set the arbitrary 0, and what we do for that is we set the arbitrary 0 the same for all of these. And so the arbitrary 0 is given at the heading of the chart here. Let's take a look at that one more time. And so our arbitrary 0 is for delta H formation, and we're going to talk about this, delta G formation and S, the absolute entropy for H plus. The absolute entropy for H plus is not really 0, but it's set or defined as 0. So that's why we have these negatives. And so the cations are going to be offset one way, the anions are going to be offset the other. So the entropies of the cations all read too low. And the entropies of the anions all read too high. And so when you add something that's reading too low in one direction and something else that's reading too high in the opposite direction, but equal and opposite, then the entropy errors cancel one another out when you add it together. And so when we form a compound, it's canceled out. All right, so we do a lot of talking just to just to figure out delta S. S. So let's go ahead and do some calculations and quantitate our delta S. So before we do the calculations, let's take a look at a couple of scenarios here. Chapter 13. Let's take a look at this here. So I have a container. Right now, all the blue atoms or blue particles are confined to the left. And then I open the valve here. This is the valve called a stopcock. Open it. And what's going to happen? Well, some of the blue atoms will move to the right here. You know, there's just going to be diffusion processes occurring. So which one of these two have higher entropy? Which one has lower entropy? And so we have the same number of blue particles here. And so which one would be higher entropy, which one would be lower entropy? Or are they the same entropy, the initial and final? So in other words, was there a change in entropy here? Now they're both gases. And so here, there are different ways of thinking about it. Here, it's more ordered, more constrained. There are fewer ways of arranging things. When I open this, I've just doubled the volume. If I double the volume, now there are going to be twice as many ways of arranging it. And so by doubling the volume here, I'm going to double the entropy. As far as positions go for this. And so here, the entropy increased. What happened to the energy? Well, the energy, there are different ways we can do this. You know, I don't know if you remember back in Chem 1A. Do you guys remember adiabatic and isothermal expansion of gases? No? Okay. Normally, when a gas expands, you know what happens to the temperature? Like, well, let's say, do you ever use one of those spray cleaners, like those compressed air, you know? It gets cold, doesn't it? Like if you're spraying the dust off the keyboard or something, it's electronically, it gets really cold. Why does it get really cold? Well, it gets really cold because you're taking the volume of the compressed gas and expanding it. That's like blowing up a balloon. When you blow up a balloon, it requires work. And in order to do work, you need energy. And so when you're spraying off, let's say the keyboard or electronics with one of those compressed air cans, it gets cold because where the energy is coming from, it's coming from the surroundings. So the surroundings is losing energy. The system's gaining energy in order to do the work of expanding the gas. And so the same thing happens here. When the gas expands here, the volume's increasing. If the volume's increasing, the system's blowing up the balloon. If the system's blowing up the balloon, then it's losing energy to do work. And so this is going to get cold. And so the energy does change. But what we do is we waited for it to warm back up. And so here, what we'll do is we'll start at 298, expand the gas, it cools a little bit, and then it warms back up because it gets energy from the surroundings. This is called isothermal. And so that we end up at the same temperature. So we start at 298, we end at 298. And so there's no change in energy, no change in kinetic energy here. And so the only thing driving this reaction is a change in entropy. And so this happens spontaneously. That is, the entropy goes up, that's favorable. Entropy going up is favorable. And so we know that this should happen spontaneously. There's a driving force for this, and that driving force is maximizing entropy. We didn't have to do any calculation there. Here, what do you think? Is it spontaneously going to separate like this? This is the way it's going to end, or is it spontaneously going to mix like this? So if we open the valve here, does it just stay separated and constrained, or does it mix? And it mixes. We know that this is spontaneously going to happen. And so what we're going to do is we're going to do this isothermally. That is, we're going to start off at 298, we're going to end at 298. So there's no change in energy. So energy is not driving this mixing. What's driving this mixing? Entropy, because the entropy of the red ones are going to increase. There's a lot more positions you can place that in, and the entropy of the blue ones are going to increase. So in this case, we don't have to do any calculations. We can just see, well, the entropy is increasing, therefore that's going to drive it, and nothing's happening with the energy. But when we get to chemical reactions, things get more complicated. When we get to chemical reactions, we could have changes in energy and changes in entropy. And how do we weigh those things out? And so let's go back to the chemical reaction that we were looking at originally. So here, if we take methane plus 2O2 gas, this is at 298 Kelvin. And then we're going to CO2 gas plus 2H2O liquid. This is going to be at 298 Kelvin. So here we don't have any change in kinetic energy, but we do have a change in potential energy. These aren't just particles, and these particles aren't changing. These particles are changing chemically in the chemical reaction. So when we look at entropy, what's happening with entropy here? Is entropy delta S going up, which would be favorable, or is delta S not changing, or is delta S actually going down, which would be unfavorable? So this is non-spontaneous. Actually, both of these would be non-spontaneous, and this would be spontaneous. So let's take a look at what's happening with entropy here. So we're going from 1 mole of gas plus 2 moles of gas, which is going to be 75 liters of gas. And then we're dropping it down to 1 mole of gas plus 2 moles of liquid water. And so we're going from 75 liters to about 25 liters. This is a calculation we did last time. So what's happening to the entropy here? It's becoming more constrained, isn't it? And in other words, the entropy is actually going down here. We can guesstimate what the entropy change is. What's the typical entropy of a mole of gas? You might say, well, a mole of gas maybe 200 to 300. Well, let's just say maybe 200. So that's a 200 and 400. This will be about 600. Okay, a mole of gas is 200, so 600 minus 200 is 400, and then 2 moles of liquid. Liquid is about what? 100?
100 to 200?
100 to 200. Maybe I should do 300. So if I do 300, 3 times 300 is 900. 900 minus 300 is 600. Minus 200 times 2 is 400. So 600 minus 200 is 400. So this is about 400 joules. Minus 400 joules. This is a total guesstimate, but that's what we're guesstimating. And so that's not favorable. Minus is not favorable. So we predict based on entropy, this shouldn't happen. And so what's driving this is it's the energy that's driving this. In fact, the energy, did I talk about delta H and delta U last time?
Yeah, too difficult to calculate. So instead we do delta H is equal to delta U minus 4.
Okay, did I talk about the relationship between delta H and delta U? Okay. Delta H is going to factor in the work done on or by the surroundings in volume. Okay. Yeah, so if we do this at constant pressure and only PV work, then delta H is going to do it. So delta H is less than 0. We're going from higher chemical potential energy to lower chemical potential energy. So this is favorable. This is unfavorable. And so who wins? Well, it turns out delta H wins in this case because we know we can combust methane and oxygen spontaneously on room temperature. So it turns out delta H wins. But in order to figure out who wins, we need to quantitate this. In order to quantitate it, we need to put numbers on it. And so when we go back to what we're looking at here, this would be way too difficult to quantitate. You know, how can you count the number of ways of arranging the blue particles in this container? Did I pass it? Yeah, I passed it. Okay, here it is. Well, all right, I passed. That's going to be way too difficult to quantitate, but counting the entropy of this shouldn't be too difficult. And so what we can do is we can quantitate this and quantitate this, but how do we compare the two? And how do we determine if the overall process is spontaneous? Because here there's conflict. One is saying one thing, the other is saying the other. And so in our last example, we're just looking at the entropy and it was saying that the reaction should go. And so let's take a look at some more examples here and then see what we're going to do to quantitate this. So if we look at number 9A here, we're going from carbon tetrachloride liquid to carbon tetrachloride gas. And so this process is called boiling or vaporization. In order to boil liquid, is that endothermic or exothermic? In other words, does it cost heat to boil a liquid or does it release heat? In other words, do you have to add heat or do you have to remove heat to boil it? In order to boil the liquid, you have to add heat. And so that's endothermic. Endothermic is increasing energy. Is increasing energy favorable or unfavorable? That's unfavorable. However, what's happening with the entropy? The entropy is increasing. Increasing entropy, is that favorable or unfavorable? That's favorable. And so we can see, well, the energy is not favorable, but the entropy is favorable. And so what we can do is we can do a calculation. In fact, we can figure out what the energy and the entropy are for this if we have the data for carbon tetrachloride. And we'll need the data for that to determine it. And so let's take a look at the data table, Appendix D. Let's see. Now, carbon tetrachloride is an organic, and organic substances are separated into a second table here. And so here I have methane and some other carbon-containing compounds. Let's go down and see if I have carbon tetrachloride. And I don't. The table ends here. So I don't have the data for carbon tetrachloride. And in order to figure out the weights of those, I need that data. And so rather than doing carbon tetrachloride, we're going to do something that we do have the data for. And then something that we do have the data for is for water. And so let's take a look at water, which is under hydrogen here. H in the data table. And we have both. So we have H2O liquid and we have H2O gas. So we have the data for this. And so we'll take H2O liquid, goes to H2O gas. In order to vaporize water, do we have to add heat or remove heat? We have to add heat. So we know that delta H for this is greater than 0. What about delta S for this? Well, let's say gases are, let's say 300, 200 to 300. Liquids are 100 to 200. So it's going to be about plus 100. In fact, let's take a look. H2O liquid is about 100. H2O gas is about 200. So 200 minus 1 is about 100. And so this is favorable. So this is unfavorable. This is favorable. And so what we can do is we can put actual numbers on those and see what they come out to. And so we'll put the numbers on here. Delta H, we can use the equations from chapter 7 to calculate what delta H is. One of the easiest is just to use the delta H's of formation. And so the delta H of formation of the products, which would be gas minus 241.8. Minus the delta H of formation of the reactants, which would be H2O liquid, which is minus 285.8. And the units for this are going to be kilojoules per mole. Well, actually, we're doing 1 mole, so the moles cancel out. They're just kilojoules. And this comes out to plus 44.0 kilojoules. So that's it. And then we can calculate our delta S under standard conditions for this reaction. The delta S for the reaction is going to be the entropy of the product, which would be H2O gas. The entropy is a 188.8. Minus the entropy of the reactants. Entropy of the reactants would be H2O liquid, which is 69.91. 69.91. And so the entropy for this is going to be plus 118.8 something. Is it? 188.8 minus 69.91. 118.89. All right, now what are the units here? The units here are going to be joules per mole Kelvin. And we're just dealing with 1 mole, so it's just going to be joules per Kelvin. Okay, so this is unfavorable by 44 kilojoules. This is favorable by 118.89 joules. Well, that's not a fair comparison, is it? And so let's convert it to, I'm going to change this to kilojoules. So this would be 0.11889 kilojoules per Kelvin. And this would be favorable here by now. And so you can see there's a mismatch here. This is unfavorable by 44, but this is favorable by 0.118. Can we compare these two directly? We can't compare these two directly. I'd like to compare these two directly, but, take a look. This is kilojoules, but this is kilojoules per Kelvin. And so we can't compare those two directly. So how can I compare these two to figure out what the driving force is? Because sometimes entropy, if the entropy is favorable, it's going to happen. But it depends on the energy here. And so in order to come up with a fair comparison, people were looking for how to compare energy and entropy. And so the point here is that this is difficult to compare as written here. Is we have kilojoules versus kilojoules per Kelvin. If we want to do a fair comparison, then this is the way we do it. And we're going to come up with the second law of thermodynamics. The second law of thermodynamics just states this, that all spontaneous processes, and spontaneous processes would have a driving force. All spontaneous processes this includes reactions, increase the entropy of the universe. And so the second law of thermodynamics we can just write simply as this: that delta S of the universe increases, that is greater than zero, means the process is spontaneous. That means there's a driving force. So the driving force in nature can be broken down into one. I have two driving forces in nature. The two driving forces in nature I have is to minimize the energy and to maximize the entropy. When I'm talking about the entropy here, though, I'm just talking about the entropy of the system. What the universe is comprised of is comprised of two things, or at least we break it up into two parts. Otherwise, the universe is too much to deal with. And the two parts of the universe that we deal with are going to be the system and the surroundings. So let's write it over here. But the delta S of the universe can be broken up into two things. That would be the change in the entropy of the universe would be the change in the entropy of the system. The system is whatever reaction or process or object of interest that we're looking at, plus the delta S of the surroundings. The surroundings would consist of the rest of the universe. So the system can be an object or reaction / process of interest. The surroundings will be the rest of the universe. So when we calculate our delta S, our system here is just boiling or vaporizing water. So we can calculate the delta S of that vaporization process here, that is, the entropy of the products minus the entropy of the reactant. But what's happening with the entropy of the rest of the universe? How are we going to calculate that? Well, that means we're going to have to calculate delta S for everything else in the universe. Is that even feasible? No, that's impossible. So it looks as if this is going to be an impossible task, but it turns out it's not going to be an impossible task. And it's not going to be an impossible task because we can relate entropy to heat and heat back states and that kind of stuff. And so I'm going to just remember these numbers, 118, 89, and 44.0. And so what we're going to end up with there is delta S of the system. Delta S of the system is very easy to calculate. Delta S of the system, we can calculate. However, delta S of the surroundings, we aren't going to be able to calculate that. But delta S of the surroundings is going to be related to heat. And delta S of the surroundings is going to be equal to Q reversible of the surroundings over T. So the entropy of the surroundings is going to be related to how much energy the surroundings can absorb, in this case, at a given temperature. And so the more energy it can absorb at a given temperature, the higher the entropy, because there are more ways it can absorb the heat, like water versus copper metal. Reversible has a specific meaning. REV means that we have to do this infinitesimally slow and in infinitesimally small amounts of heat. So this just comes from thermodynamics. But we're also going to use the first law of thermodynamics. And the first law is energy is neither created nor destroyed. So if the surroundings is losing or gaining heat, then the system must be doing the opposite. And in other words, delta S of the system plus a minus Q reversible of the system. So this just means opposite sign. So if Q of the surroundings is positive, then the system must be negative, or if Q of the surroundings is negative, then the system must be negative times negative, which is a positive at a given temperature. And then we use the definition of enthalpy. What is the definition of enthalpy? Do you guys know how enthalpy is defined?
U of the system plus PV of the system.
Oh, okay, that's correct. There's other ways we can think about it too. Delta U is equal to Q plus W. So if there's a change in total energy, that change is going to be, whatever heat's exchanged or whatever work is exchanged with the surroundings. Q, the amount of heat, is equal to delta U minus W. And so this is the heat, but the heat, these are not state functions. Q and W are not state functions. You know what a state function is? Delta U is a state function. Okay. Well, we'll have to talk about this next time then. So we'll continue.